A host sends a packet and it reaches the destination. How does this magic happen? One of the earliest and widely used routing protocol is the RIP protocol. This protocol is based on distance vector routing algorithm. So that's the focus of this video. What comes next? You know it. Routing is a very important functionality at the network layer. Mainly its job is to find the least cost path between nodes. We have seen that there are many approaches to routing. We will focus on dynamic distributed algorithms. So distance vector algorithm is one such algorithm. We will cover it in detail. This algorithm also goes by the name Bellman-Ford algorithm. These two were the inventors of this algorithm. This was the algorithm that was originally used in the very first packet switching network, ARPANET. Later in internet also this algorithm was used, but it was used under a standard, stands for RIP, Routing Information Protocol. While it was very popular earlier, these days it is not used much because of reasons which will become apparent soon. So this is how the algorithm works. To begin with, a given node knows the distance or the cost just to its neighbors. So that's the state at which each node begins with. As the algorithm iterates, a node gets to know the distance to all the nodes in the topology. Not only this, it also knows to reach a given destination, what is the next hop. Whenever we want to implement an idea as a protocol, we saw earlier that we need to handle these three questions. First is what information do you need to exchange? This boils down to the message format. Once a node receives a message, what should it do, the action portion of it, and when should such messages be sent? And when you're executing a protocol, you also need to maintain state. So what is the state that this routing algorithm maintains? Basically the following. Each node maintains what is called a routing table. This is also called a distance vector. So here is the state that it maintains. It consists of three components. One is the destination. Another is the estimated cost to the destination. I would like to emphasize on estimated because it doesn't really know the exact cost. It is making an estimate, and as the algorithm proceeds, this estimate will converge to the actual cost. And to reach the particular destination, which hop should it take to? As I mentioned, this is the initial routing table at B. So it has three neighbors, A, C and E. So the initial routing table corresponds to the three neighbors, and it is a cost of 139. Since it can directly reach them, the next hop also happens to be these neighbors themselves. It's a rather boring calculation, but still tell me what is the final routing table at B. Just look at the figure and do the calculations manually. So here is the answer. This topology was small, so you could quickly calculate this final routing table, but when the number of nodes are really large, you need a very efficient algorithm that does these iterations to get at the final routing tables. So that's why we are studying this algorithm. This is the state maintained. Getting back to the protocol, what is the actual message content that is exchanged? So each node exchanges with all its neighbors. Let me emphasize that this is just neighbors. It is not exchanging with others, only the neighbors. It's routing table information. That is the destination and the estimated cost to the destinations. Well, it should be destinations because a node can maintain information about many destinations. Note that the next hop information is not shared. So for example, B here exchanges only this information to its neighbors A, C and E. Now once a node receives this message, what should it do? So this action is based on the Bellman-Ford equation. Suppose this term here represents the least cost path from node X to Y, and let me represent by V the set of X's neighbors. The least cost path from X to Y is dictated by this particular equation where the minimum is taken over this entire set of X's neighbors, where you will determine what is the cost of going from X to this neighbor. Let me call it A. What is the cost of this? So this is CXA, and then what is the cost of reaching this destination Y from A. Then taking the summation of the cost from x to the neighbor and the least cost path from the neighbor to the destination y, and taking the minimum over all such possibilities is what is going to yield the least cost path from this node x to the destination y. A node really doesn't know the actual least cost path. It has an estimate, so it starts working on the estimates, and as long as you're taking the minimum, it converges finally to the least cost path. So basically here is what happens. So on receiving a message from a neighbor v, this is what a node does. It will update its cost based on this particular equation. So this neighbor v said that it can reach y at this particular cost. It already has an estimate. Maybe this estimate was determined based on some other neighbor or its initial state information. Then what it does is it adds the cost of reaching the neighbor v, so that is cxv. So this is the total cost of x to y if it were to take the next hop as the neighbor v, and this it compares with its current estimate, and it will update the current estimate with the minimum of this value. So after this step, the current estimate will be equal to dxy. And as it keeps hearing from the neighbors, this estimates keeps on revising. The neighbors themselves are hearing from other neighbors, so it finally, through this message exchange, it converges. So nothing like an example. Let's see how this works. So we are focusing on this node C, and this is the initial routing table of C. As I mentioned earlier, it maintains information only about its neighbors A, B, D, and these are the costs respectively. And the next hop, since it can directly reach them, these next hops also correspond to the destination. Now suppose C were to receive a message from A, and this is nothing but the initial routing table at A. So that is what A sent, and now C is going to act on that particular information. It knows that the cost from itself to A is equal to 5. So what it does is it is going to add this 5 to all this information and compare it with its current estimates. If this information is giving a better cost, it is now going to replace the next host via A and change the cost also accordingly. So let's see step by step. So here it is directly connected to A. This is what this is also telling. So this information does not change. So currently it is directly connected to B and it has a cost of 3. Now it can also reach B via A, and this is a cost of 5 plus 1. So this is equal to 6. But this number is more than its current estimate. So it will retain its current estimate and keep the next hop as before. It doesn't act on this because we are focusing on node C itself. D, it didn't even get any information, so it will retain the previous information that it had. So after receiving a message from A, this is going to be the routing table at C. Suppose node C were to receive a message from B with its initial table. So this again is the initial routing table of B, and the cost from C to B is 3. And again, you should do the same procedure where you try to determine whether its current estimates are better or whether B can provide better paths. Do the calculations and figure out what the routing table at C is going to be after this step. So let me just do one step. Let's look at this destination A. So node C has a cost of 5 to A according to its current estimate, but B is saying I can reach A at a cost of 1, but the C to B, there is a cost of 3. So 3 plus 1 is 4. This is better than the previous estimate. So it is going to update it with this information where it says I can reach A at a cost of 4 via B. So that is how it had updated. Now it heard new information here which it didn't have. This also it has made note of. So the same step happens when it receives a message from D. You do the same process and you can arrive at this. So as messages keep coming at node C, it is going to update its cost. Not just at C, this is happening at all the nodes. And as new routes are discovered and as the cost metrics change, they are going to exchange their new information to the neighbors. Thereby the neighbors also are going to change their estimates. So here are a few points to note. If there was no topology change while you're running this algorithm. The nodes converge to the final cause in just a few rounds. Basically, what happens is after one message exchange, by the way, when I say one message exchange, I don't mean that there was one message transferred in the network. Rather, every node has exchanged one message with its neighbors. After such an event, each node knows about nodes 2 hops away. So why like this? Because from the perspective of this node, let me call it A, its neighbor has given information about nodes that are 1 hop away from it. Thereby, A now knows about nodes that are 2 hops away. By the same count, this neighbor, let me call it B, also got to know about nodes that are 2 hops away from it. Now, when another round passes, B is now going to convey information about nodes that are 2 hops away from it. Thereby, A gets to know information about nodes that are 3 hops away. So, this kind of progresses. So, does this algorithm fall under the global knowledge or the local knowledge approach? Local knowledge approach. No node has any idea of the entire network topology, that is, who are the neighbors of any given node. It knows only about its neighbors and through message exchange has determined route to the destinations. So this is a fully distributed algorithm, yet it maintains correct view. Going back to the protocol, we have seen what messages are exchanged, the content of the message. Next, we have seen how does a node act once it receives a message. Now we will see when does a node send a particular message. What do you think? When should a node send a routing message to its neighbors? Naturally, whenever the distance vector, the routing table changes, you need to inform your neighbors of the change in the metrics. So this happens whenever a link node fails or the cost increases. So these are called triggered updates. But often a node also sends periodic updates even when the distance vector does not change. Why do you think this is needed? Well, for one, this informs the neighbors that this specific node is still alive. But for this, it is not necessary to include the routing information. More importantly, this is done to ensure others can find an alternate route if some route had become invalid. What do I mean by this? Let me give an example. Suppose this was the specific network topology where all the link costs are equal to 1 and this link has failed. Thereby, the cost has become infinity. Let's now assume that there is some mechanism based on which A will detect that this link has failed. So its distance vector, so the cost to C at A is now set equal to infinity. Now this is going to do a triggered update and based on that it will send a triggered update to B. Now B is going to ignore that particular triggered update because it is anyway has a cost of 1 to C. It is directly connected to C. Now if B kept quiet, how will A ever find an alternate path to C, which is this? Nothing really changed at B, so it is not going to generate a triggered update. Only via periodic update will A get to know about this alternate path. So such periodic updates are sent ranging from a few seconds to few minutes. It's a configurable parameter. Since we are talking about node or link failures, how does a given node figure out that something went wrong? Either this link failed or let's say this node has failed. How does it figure this out? Well, since anyway we are sending periodic updates for the more important reason, we might as well leverage on this and view these as keep alive messages. That is, if I don't hear a periodic message from a given neighbor for some time, then I will conclude that either the link or the node itself has failed. One could also actively probe a neighbor by sending probe requests, and it is expected this neighbor is going to act this probe request. There is more to distance vector. However, let me stop here. So here is a quick summary of what we have seen in this video. So we looked at a dynamic distributed algorithm called the distance vector that works with local knowledge. This algorithm is based on the Bellman-Ford equation. Basically, each node iteratively through message exchange with its neighbors refines the cost to all the other nodes in the network. This algorithm can also handle node and link failures. As we have seen again and again, there are always going to be issues with any idea. So up ahead, we will see some problems associated with distance vector as well as some solutions to the problems and the standard that implements the distance vector algorithm.